Hello, everyone. My name is Riley Dickens, and I'm a consultant at Encryption Consulting. Encryption Consulting covers all the aspects of security concerns, including data security, key management, and data privacy. Today, we will be going over the concept of post-quantum cryptography. We'll start with the introduction and then dive into a more detailed breakdown of this technology, along with its use cases. Post-quantum cryptography, in the simplest of terms, is a group of approved algorithms that gives protection from any hacking being done with a quantum computer. This is a hypothetical situation as of now, since quantum computers are still in development. However, based on their current progress, sooner or later it's going to be a risk. Keeping in mind the sheer power of a quantum computer, it's suggested to be well prepared for such a situation. To understand what post-quantum cryptography is, we first must understand what quantum computers are. Quantum computers are the next generation of computers that are being developed by utilizing the concepts of quantum mechanics. Quantum mechanics is a branch of physics that deals with subatomic particles. It is theorized that particles can exist in multiple states at the same time, leading to the idea of Schrodinger's cat. Now, let's discuss how a quantum computer differs from a traditional computer. A traditional computer is an electronic device that deals with bits which can represent either the value 0 or 1. Quantum computers, however, work with quantum bits or qubits. A qubit can have the value of both 0 and 1 simultaneously. This doesn't necessarily increase the computational power of a computer. However, it does increase the speed exponentially of computation in certain cases. One of these cases is prime factorization, which can be used for decryption. If a traditional computer has 10 bits, it can have, at most, 100 outcomes. However, in the case of quantum computers, a 10-qubit system can have 2 to the 10th power, or 1024 outcomes at a time. The important thing to note here is the time it would take to crack the traditional computer's algorithm. Since each qubit can have 2 values, 0 or 1 at the same time, this makes quantum computers a tremendous brute force machine, allowing them to search through multiple combinations at the same time and give instant results. Being this fast, a quantum computer poses a threat to any system in the cyber landscape. This means all financial, healthcare, and consumer data could be at risk. Now that we have an idea of the threat, we need to be ready with controls to tackle this threat. This is where post-quantum cryptography comes in. These are cryptographic algorithms that are a step ahead of the currently available public and private key-based cryptographic algorithms. Organizations such as the U.S. National Institute of Standards and Technology, or NIST, are actively seeking applicants to submit various algorithms which can be considered quantum proof, quantum safe, or quantum resistant. The target is to standardize these algorithms and rate them based on their computational efficiency, memory requirements, and ease of implementation. To date, we have very few algorithms which are considered quantum resistant, but organizations such as NIST are trying to increase their arsenal. A few examples of currently available quantum-resistant algorithms are lattice-based, code-based, hash-based, non-commutative, multivariate public key, and supersingular elliptic curve isogeny-based cryptography. These are highly complex algorithms, much more complex than algorithms such as AES or SHA-3. As I mentioned, these are extremely complex, so for this video, I'll just give a brief overview. Let's start with the first one, lattice-based. With lattice-based cryptography, cryptographic primitives that involve mathematical lattices are used. A lattice can be thought of as any regularly spaced grid of points stretching out to infinity. With code-based cryptography, the algorithmic primitive may consist of adding an error to a word of C, or in computing a syndrome relative to a parity check matrix of C. In hash-based cryptography, cryptographic primitives are constructed based on the security of hash functions. Non-commutative cryptographic primitives, methods, and systems are based on algebraic structures like semigroups, groups, and rings, which are non-commutative. With multivariate public key, asymmetric cryptographic primitives are based on multivariate polynomials over a finite field. Finally, there is supersingular elliptic curve isogeny-based cryptography. Rather than working in the group of rational points on a single elliptic curve, it works with isogeny graphs of supersingular elliptic curves on a single finite field. Just like we build dams for a potential flood, it's important to build security controls for a potential quantum computer-based attack. To give more perspective, the financial industry, healthcare industry, and defense sector could all be crippled by a quantum computer. Since it's more than just the ability to crack encryptions, this is due not only to the fact that it can crack encryptions, but also that quantum computers can do it at a rapid pace that is so much faster than a traditional computer. Post-quantum cryptography, however, is a preventative mechanism. It prepares us for the era of quantum computing by updating existing mathematical-based algorithms and standards. So not only does it make us more vigilant, but it also makes our existing security landscape more robust and efficient. Every industry deals with sensitive data, be it in the form of PII, PHI, or competitive data. With the hypothesis that all data protection mechanisms, such as encryption, could be cracked by a quantum computer, the use cases of post-quantum cryptography become countless. Firms with critical data need to start developing crypto inventory and map all their existing cryptographic algorithms being leveraged. This inventory will be critical during implementation of post-quantum cryptographic algorithms. According to various security agencies, the threat of quantum computers is not an urgent issue, since it takes a lot of resources and millions of dollars to build just one quantum computer. This threat, however, is inevitable. Organizations should start implementing these algorithms much sooner than later. It is also important to keep developing these algorithms. The initiative by the NIST to standardize post-quantum cryptography is a necessary and important milestone in data security. Even more effort should be put into keeping in mind the impact of the risk. That's the end of our video for today. Thank you for watching, and if you liked it, please leave a like and subscribe below. Visit our website, encryptionconsulting.com, if you have any questions or there's any other data security terminology you'd like to learn. Thank you.